Okay, this is going to be the second part video for chapter 20 for AP statistics. In the first part, we covered all the main idea behind how hypothesis tests are done, which is the idea that what you're studying becomes the alternative hypothesis, HA, and then you make a null hypothesis where that is not true, or the dull hypothesis, nothing unique to see here. And then you try to use your evidence to show whether or not the null hypothesis can be rejected, right? And if you can reject it because the p-value is less than 5%, then you say we do reject the null hypothesis, so therefore we do have evidence that there's an alternate hypothesis explanation. Just to kind of review that, let me just take us back real quick and talk about the fact that we have a population that we're studying, right? And we have a parameter for the population. In this case, it would be p, the percentage of yes in the total population we're studying. We have a sample, right? That's p hat. That's called the statistic. Okay, so this is the parameter that we're estimating or investigating, and this is the statistic from the particular sample that we take. And then the way we determine whether or not this is unusual compared to this is we make an assumption about what this is, right? So we make an assumption about what the population value is, and we call that the null hypothesis value. So what we do is we say, all right, we're going to make an assumption that the population value is p0, and we center a normal curve at that. Okay, that's the null hypothesis value. And then we have our particular thing that happens, right? This is p hat, right? So that might be above or below. Like say, we don't expect it to land right on this, even if this is true, right? But then we find something called the p-value, right? And the p-value is the probability of getting this statistic this far away or further from the assumed value just by chance, right? And we usually use normal CDF to compute this, right? That's called the p-value. And I'll always put dash value here to keep it separate from this p, which is the percentage of yeses in the population. So we have the population level, we have the sample level, and this level down here is called the sampling distribution model level. Okay, right, so we use the sampling distribution model, and the key idea there is that we know the standard deviation down here because we can estimate it. We're going to estimate it, standard error, by saying it's the square root of PQ over N, but what we use is the null hypothesis value for that, right? So we can control how much variation we would get from sample to sample by increasing or decreasing the sample size, right? All right, so that's the idea, and this is called inferential statistics because we're using the sample to infer things about the population. All right, so yesterday we looked specifically at this value here, and maybe we would get something like 0.14. There's a 14% chance that this happened randomly, and therefore we would say, all right, if that's, then we would say with a significance level of 5%, which is our boundary for deciding whether or not something is unusual, p-value equal 0.15 is high. It's above 5%. So we fail to reject the null hypothesis, right? So the logic was, if this is not unusual, then that means we have no evidence to reject that this is really the center. Okay, therefore, we do not. If we fail to reject the null, then we do not have sufficient statistical evidence. I'll abbreviate a little bit here. To conclude, and then we write out whatever the alternate hypothesis is, the thing that we were investigating that might have been true. All right, so the next thing we're going to talk about is, what about this level right here? Why is this 5%? Okay. Well, the reason it's 5% is just due to history, right? The person who invented this was Sir Ronald Fisher, and he had to pick something he thought 1 in 20 was unusual, and so he set it at 5%. But the truth is that that's a fairly arbitrary value. Why is that the cutoff value? Just it happens to be 1 in 20 chance. It's a rule of thumb. It was proposed by the first person that conducted this, right? But the truth is, the cutoff for deciding whether something's unusual enough for us to consider it to be statistically significant, that should actually depend upon the particular situation. 5% is frequently used, right? But you could either make it larger or smaller. All right. So, for example, let's say that I'm just interested in the proportion of college students who hold part-time jobs, and we're investigating whether or not there's a claim that the percentage of college students who hold part-time jobs now is higher than in the past. Maybe we could even go up to 10%. Like it could, anything below 10% we would consider unusual because, a 10% chance of something happening is fairly unusual, right? Why is it 5%? Maybe we could go with 10%, right? But on the other hand, if you're trying to do something that's extremely important, like assessing something for the safety of an airplane, let's say, or I'll give you another example. A theoretical physicist experiment is testing a new hypothesis in particle physics, which, if true, is going to change our understanding of the universe. Well, you don't want there to just be a 1 in 10 chance of that happening randomly and us concluding that that's true. So we would have to go with something a lot lower, even than 5%. In fact, particle physics research, their cutoff value for deciding something's unusual is there has to be 5 sigma. In other words, you have to take whatever the standard deviation is here. And 5% is about 2 standard deviations below or above the mean. They require that you're 5 standard deviations away to be considered unusual enough to be considered statistically significant for a particle physics experiment. So this value can change, but the truth is this is by far the most common value. Okay, so we often use that value. But if you have some reason or justification for changing it, making it higher or lower, you can do that. In fact, we'll investigate what happens when you do change it in the next chapter. All right, so this cutoff value has various names. The most common one is significance level, and that's what we're calling it now. So that is how low does the chance of something happening randomly have to be for us to say it's unusual? Okay, significance level. Another phrase for that is alpha level, because in the next chapter, we're going to define this symbol to indicate it. So a lot of times it's written this way, alpha equals 0.05, because alpha is the statistic symbol for significance level. And then another one is a kind of a more loose phrase called standard of proof. And the idea is, what would it take to prove you? What's your bar, your standard of proof to convince you something's unusual? So lower significance levels, lower alpha levels correspond to a higher standard of proof. Okay, with that much of an introduction, we can go ahead and do required practice packet, the second page. So I'm going to ask you to take that out next. And we're going to go ahead and go through that together here. Okay, this is actually intended to be kind of a group investigation, but since if you're watching this video, you're probably doing this at home by yourself, I'm just going to go through it step by step. And it involves using your phone to access one of those applications again from my website. So if you go to mrfelling.com/SA3, that's statistics activity 3, so /SA3, you'll come to a page here. I'm going to display it over here on the side. Okay, you'll come to some screen that looks like this, the meaning of p-value. Okay, so we're going to go ahead and just do this. It says read the whole page on your phone, and then we're going to select one-sided upper, which is what the default is, and then we'll click samples. So you can do this with me. You can just watch if you want. We'll read the whole page and we'll record the values that we got for our particular trial. Okay, so it says the historic value for proportion of DV seniors staying in state for college is 78%. Okay, test the hypothesis that more students are staying in state this year by taking a sample of 50 DV seniors. Okay, that means that the null hypothesis would be that the proportion for the population P of DV seniors is still equal to the historic value of 0.78, or in words, the proportion of students staying in state for college hasn't changed. It's still 78%. But we're testing the hypothesis that more students are staying in state because of the phrasing here, more students. So the alternate hypothesis, HA, would be P is greater than 0.78. More than 78% of students are staying in state. So on your sheet here, your required practice packet, you can fill in the hypotheses. For HO, we would say P equals 0.78, and in words, we would say the proportion of students staying in state is still 78%. Okay, so that's the Null hypothesis, the dull hypothesis, nothing has changed. The alternate hypothesis that we're investigating might be true is that P is something greater than 0.78, that more than 78% of students are staying in state for college. Okay, so that would be HA, the alternate hypothesis, the thing that would be unusual if it was true. Okay, so now we're going to run a trial, and it says here's a kind of a picture of the population. So we would not know this actually. So I've programmed this thing to say that actually in this particular group of students or this year of DV seniors, 84% of them happen to be staying in state. But we typically would not know this. So this is something we don't know it, but the true population proportion for this year is not 78%. It's actually 84%. Okay, so what that means is the samples that we take are going to kind of cluster around this value because this is the true value. Okay, so we take a sample of 50 DV seniors and we find the percentage of them that stayed in state. Now, when I ran this, I got my p hat value is 90%. So I'm going to report that for my sample over here, that I had 0.9 as my p hat value. 90% of my 50 seniors in my sample are staying in state for college. Now, when you run this program, you're going to get something different. So you want to write that value down here. Okay. The null hypothesis value is what we're assuming. Now, what we're assuming is not the real value because we don't know this 84%, but we're assuming that it's 78%, the 0.78 that it has always been. Okay, so we take our sample, we get 90%, and we compare it to the null hypothesis value to judge whether it's unusual. So here's that sketch of the sample for a sample size of 50. We can calculate the standard deviation. The program does that automatically, and it puts the 90% here down here. This red line is where our particular sample is. Mine was at 90%, yours is somewhere else, and this is centered at our assumed value, 78%. Okay, the p-value would be shaded to the right because our null hypothesis is greater, that p is greater than 78. So we're going to shade to the right. And you can't really see it on mine here, but there's a little green fill in here. And it calculates the p-value with a normal CDF function and gets 0.0228. So I'm going to fill that in over here, 0.0228. Now your value would be different, okay? Okay. Then the way we would finish this problem is, because this p-value is low, below our standard 0.05, it's unusual. So we would say with significance level of 5%, a p-value of 0.0228 is low, so we reject the null hypothesis. It's too unusual to assume that 78% is still true. And therefore, the second sentence in the paragraph would be, we do have sufficient statistical evidence to conclude that more than 78% of students are staying in state. Another thing that we sometimes get asked on AP tests is to explain what the p-value means. So that also has a standardized way to write it up, and it would look something like this. If 78% of DV seniors were actually still staying in state, our p-value of 0.023, or whatever yours is, means that there's a 2.3% probability of having a sample of 50 students with 90% that we had in our sample staying in state, or larger, just due to natural random sampling variation or just by chance. Okay, so then we're going to click this twice again. So you can do this with me at home. I'm going to click sample again. Now, the write-up here is the same. It's the same problem. So our null hypothesis has not changed. It's still 78%, right? But because I took a different sample of 50 seniors, I've got a different percentage. In this sample, it happened that 82% of the seniors stayed in state for college. And because this is now not as far out, there's a larger area of shading here, right? So the p-value is larger in this case. It was 0.242. Now, yours would be different, of course. You should write down your values here. Now, in my case here, that means that now I'm at 24% chance of happening. So this is no longer below 0.05, right? My p-value in my first run was below 0.05, 0.02. So that was statistically significant difference. But my p-value this time is 24%. That's not below 0.05, so therefore not unusual. So if you get a result that's above 0.05, like this one, Then you write it up this way. With significance level of 0.05, a p-value of 0.242 is high, so we fail to reject HO. Therefore, we do not have sufficient statistical evidence to conclude that more than 78% of students are staying in state for college. And if you're asked to explain what the meaning of p-value is, you can say it like this. If 78% of DV seniors were actually still staying in state for college, our p-value of 0.242 means there's a 24.2 probability of having a sample of 50 students with 82%, it should say or more, staying in state, this sample's value just due to natural random sampling variation. All right, and let's do it one more time. So I'll do this again. And again, the null hypothesis is not changing, 0.78, but every time I run a new sample, I get a different p-hat. This time I had 0.76, so that moved even further over. In fact, it moved below the null hypothesis value. That's okay. That just means that there's a greater than 50% chance of it happening randomly. P-values don't have to always be below 50%. So this time my p-value is very large. There's a 62% chance of this happening randomly, right? And of course, that would mean that we would conclude that this is definitely high enough to occur by chance. Therefore, we don't reject the null hypothesis. Therefore, we don't have evidence that there's been a change. Okay, so usually at this point, after I've had people fill this in, I have people just discuss, what has stayed the same and what's changed. So I've already been talking about it as we've been going over it. What stays the same each time is the null hypothesis value, right? So maybe we could write this. What stays the same is the null hypothesis value. That's set by what we're investigating, but it's not based on the sample. It's based on our question that we ask. Is it the same as before, or is it larger? Okay, but what changes each time is the particular p-hat value, right? Because that's based on the percentage of people that stayed in state this particular year in this sample. So every time I take a different sample, I get a different value. And therefore, the p-value also changes, right? Because that's based on shading from this value as a boundary. So when you move the boundary, the p-value changes. Okay, and then if we continue through the questions, it says, why are your p-values different? You could pause the video and take a second and think about this, right? Why are they different? Because I would say the reason why they're different is because each sample is different, right? The p-value is based on that. And how are the p-hat and the p-values related? If I would say this, if p-hat is above the null hypothesis value, then when p-hat increases, in other words, if I go further out here, then the p-value decreases, right? Because the further away you get from the null hypothesis value, the lower the p-value, okay? Okay, now we're going to do something different. Okay, and this is something a little different. We're going to click reset, and then we're going to run this program again, but this time we're going to select one-sided lower, okay, and see how that changes the problem. Okay, so it says, test the hypothesis that fewer students are staying in state this year by taking a sample. So what would cause us to write our null hypothesis this way is if the wording asks us not whether more students are staying in state, but fewer students are staying in state this year. So because they're asking us to investigate fewer, that means that the null hypothesis is going to stay the same. It's going to be that the proportion hasn't changed, but the alternate hypothesis is going to be that the true proportion in the population is now less than 0.78, fewer than 78%, okay? We would still have our null hypothesis value, or whatever it was, 0.78, but now maybe the population value, if our assumption was right, wouldn't be up here at, say, 0.86, it would be somewhere low, like maybe 0.72, something below the null hypothesis value. So we take our sample proportion, it's going to be something fairly near where the real value is. But here's the big difference. When we have an alternate hypothesis that's based on fewer, and so it's less than, when we take our boundary for p-hat, we always shade to the left of that value to find with the normal CDF function, okay? And then again, if this shading, like in my case here, was 15%, 16%, that's not lower than 5%. It's not unusual, so we fail to reject the null, so we don't have evidence that there's anything unusual going on. Okay, so the big idea here is when it says compare what you see is I would write it this way. If you have fewer in the wording, then that means that the alternate hypothesis changes to P is less than the null hypothesis value, 0.78. Okay, and we shade to the left. Okay, so if we have wording that says more, we shade to the right. If we have wording that's fewer, it's shade to the left. Okay, there is one other idea. Let's go to reset, and let's click two-sided. There's a potential typo in your thing here. This should say for F, two-sided. Let's look at the wording here. It says the historic value for a proportion of DV seniors staying in state is 78%. Test the hypothesis that the percentage staying in state this year is different from 78%. So this just says it's different, but it doesn't specify whether or not we're investigating that it's specifically more or specifically less. It could be either one. Okay. So the first thing that happens is the alternate hypothesis changes. It's no longer greater than or less than. Now it's just not equal. It can be not equal either on the upper side or the lower side. The proportion of students staying in state for college has changed. It's just different, but we don't care whether it's above or below. Okay, we get our p hat value. So how do you shade in this case? So this is a little bit unusual, but what we do is whichever side of the null hypothesis value the p hat happened to be on, we shade on that side away from the null hypothesis, and we get that value from normal CDF. But then what we do is, because it could also have been below, we double the p-value to account for the fact that it could have been below. This one happened to be above, but it could also have been below. So whatever we get here, we double it. And the program's automatically doing that. Okay. But we still use the same 5% to determine that. So what that means is that both these shaded areas together have to add up to something that's less than 5% to be able to conclude that this is different and statistically significant, because it's unusual. Okay, so what would I say that what we see compared to the other, if you have different from or different than wording, then HA changes to not equal. In other words, P is not equal to the null hypothesis value. And we shade away from HO, from the P0 value, for whichever side P hat is on. Then we double the calculated p-value to get the other side. All right. So just something to kind of walk through, something that I think we need to see in practice. Okay, let's go back to the notes. Now that we've done required practice 2, I want to mention that let's kind of summarize what we said there about the shading. So there's three ways to shade. There's one-sided alternatives, and there are two-sided alternatives. Okay, so the first case is if we have wording that says more seniors are staying in state, then we make the alternate hypothesis greater than, right? The null hypothesis is always equal. That this would be, and then when we shade to the right of the p hat boundary value. Okay. But if the wording in the question asks, do we have reason to believe that less seniors are staying in state, we make HA less than, and then whatever p hat value we have, we shade to the left of that, regardless of what side it's on. On the other hand, if we have something that says, do we have reason to believe the seniors staying in state has changed, that doesn't specify a direction. That's called a two-sided alternate hypothesis. And therefore, we write it using p is just not equal to 0.78 without specifying a direction. Whatever value side p hat's on, we take the shading away from the null hypothesis value, and then we double that value to pick up this other side over here. Okay. All right. Okay, another thing that I need to mention here is the idea of statistic versus test statistic. So we said that the statistic is what we find in the sample that is, in this case, like the p hat value. Okay, and we can use that directly in normal CDF. You can put the p hat value here as a boundary, in this case to infinity, right, with our known mean and standard deviation to calculate the p value. Okay, all right. But if you wanted to, what you could do is say, let's take the value that we got, our p hat value, and let's subtract that from the null hypothesis value, and then divide by the standard deviation that we calculate for p hats. In other words, we could take that same 0.85, say the null hypothesis value was 0.78, say how far away was that, and then divide by how big a standard deviation is to get a z-score. Now, if you do that, then this is not p hat any longer. This is a z-score that corresponds to a p hat. And then instead of calling it a statistic, we call it a test statistic. Okay, so if you see the word test statistic, it means the statistic, but converted to a z-score. Then it's called a test statistic. And you can still use a normal CDF function. You would use the test statistic z to infinity, but you would use 0 for the mean and 1 for the standard deviation. You get that same value. That's not important right now in the course, but when we get later on, it's going to turn out that a lot of times we have to convert things to test statistics. But for right now, you can either use the statistic or you can use the z-score version of it, the test statistic. You just got to make sure you use the right mean and standard deviation. Okay. All right. So we've done required practice number 2 here. The next thing we're going to do is take a look at required practice number 3. And I think, yeah, we can go ahead and finish this so that it doesn't require a third day. Yeah, there's not that much more to go over here. Yeah, we're going to go ahead and do this now. Let's see, how long have we been going? No, I'm going to put this next part in a third part just in case it spans to a third day. So we'll end this session at this point. This is the end of part 2.